Hi, and welcome to Maths Appeal. I'm Bobby Seagull.
And I'm Susan Okereke.
And the aim of this podcast is to celebrate maths.
We know that for many people, maths is a bit scary or boring, so we want to show how fun it can be.
This is episode 11, a prime number. And if you've missed the early episode in the series, you've missed out on our chats with guests like Johnny Ball, Dr. Anne-Marie Maffedon, and Mike Ellicott, CEO of National Numeracy.
You've also missed out on discussions about algebra, statistics, and percentages, and a whole load of puzzles created by our very own puzzle king, Bobby Seagull.
The Puzzle King. There's a puzzle in this podcast right after we've chatted about 2D and 3D shapes. And our guest today is Catherine Breslin, a machine learning scientist who's worked in voice recognition with smart speaker devices like Alexa.
So we've got loads to get through. And let's start off with 2D and 3D shapes.
So each week, our discussion topics are split up into 3 different parts. For this week's 2D and 3D shapes, the first question is what comes to mind when we think of the topic. Then secondly, how do we teach the topic, introduce it to students. And thirdly, what are the common issues that arise when teaching this topic? So Susan, I'll kick you off. So what comes to mind?
Right, so this topic is just so huge, but I really enjoyed teaching it, but wish I taught it better. I know that is truth. A key thing to probably define is what does 2D and 3D mean? And because I know kids know the letter and number together, but they understand that 2 dimensions is flat and 3 dimensions is kind of the world we live in, is kind of popped up.
Yeah, and 1D is a cool band.
Or a dot.
Or a dot, yeah.
Yeah. And then it's funny as well whenever you sort of think about it. So there's 1D, 2D, 1D, and 3D. But then the issue, I suppose, is 4D. What does that even mean?
Yeah.
But we don't. That's a much bigger conversation. But that whole idea in maths, so it's an extension of what we talked about last episode on lines and angles.
Yeah.
And it's kind of where you you join together sort of loads of angles. Lines that create kind of angles, and then there's the namings of those. So it's like polygons where you've got like more than 3 sides. And I love going through the names of polygons because then I generally connect it to our calendar months.
Oh, okay. So how do you mean that? So like we've got January.
Well, right. So it's the latter.
Oh, I got you. December. I got you.
Right. So this is how I would generally. So we look at polygons and the relationship with angles, and then I always get them to sort of name polygons. And the way I get the kids to remember it is I go into the story of the months. There were 10.
Yeah.
And then Julius Caesar added in 2 months, July and August. And so it used to be that September was the 7th, October was the 8th, November was the 9th, December was the 10th, just like the actual prefixes of the words.
But Julius Caesar messed it all up.
Yeah, but it was crazy because you'd have thought that if bring it in and just keep the months in, that actually coincide with the number of the month. So it's kind of a really mad mistake to make.
Yeah.
And then when you know that septagon is 7 sides, octagon 8 sides, nonagon 9 sides, decagon 10 sides.
So we've got the 2D shapes. And again, they can see them quite flatly. But the 3D shapes is where...
Oh, wow.
Yeah, you need to bring out the physical objects for people to see. So again, every shape. So we've got let's say the triangle.
Yeah.
And you might think of...
3 angles.
How do you make that into a 3D shape? It could be a square-based pyramid, or it could just be a tetrahedron.
The faces,
triangle on each side.
Yeah.
Or then we've got the cube, which is what most people know. The cube, which is just a square on every face, so 6 sides, a dice essentially.
Yeah, I think it's that whole defining of, with the 3D shapes, you've got like pyramids where there's like a base shape, which is like, it can be a square or a hexagon or whatever, but it comes to a point. So the whole point is a pyramid has a pointy top, and then you've got prisms, and it's like a flat shape, like a square or a circle or a triangle that has been stretched like a loaf of bread. So, and then when you slice it, it's the same faces all the way through.
Like a slice of cheese. If it's like, I always tell my kids, a prism, for it to be a prism, you have to imagine like a cheese. And if you slice it anywhere across, everyone will get the same slice of cheese.
Oh, okay.
On one plane. So if I slice it, let's say 1 centimetre from the edge or 20 centimetres from the edge, that slice along the same plane will still look the same. If it doesn't, then clearly it's not a prism, because a prism has to be the same all the way through.
Like a Toblerone, that kind of, that's that whole idea of it's a shape that has then been stretched backwards, and you slice it, and then the faces are the same. But I suppose there's the whole just like naming them and understanding them and looking at these massive relationships and properties of these different shapes. But the key thing, like I like to learn it, but it's a lot to deliver, because then you've got, in 2 dimensions, you've got the different names of the shapes, but you've also got things like working out the perimeter, which is the length around the outside of the shape. And then you've got working out the area, which is the space inside that 2-dimensional shape. And there's different formulas for that. And actually, what's a bit of a shame is that when I deliver it in school, there's not much time. I think really the key thing is to spend more time playing around with these things and the students to actually be touching them and creating them, and especially with the 3-dimensional shapes, as you were talking about, because then you go from the 3D shapes, looking at them, and there's the different things to look at, like the surface area, so the area around the outside of the shape, like you're wrapping it in paper, and then you've got the volume, which is for you to the space inside that 3-dimensional shape, like you have to fill it up with water. So there's a lot of different things to kind of remember and think about when you're looking at shape when it comes to learning stuff in school. And then what I want to really try and do is to spend more time and talk to design technology teachers, because they, use this maths in creative ways to create and make things.
Nets or...
Yeah, no. You think about, the cereal you eat in the morning. It's a cuboid, but there's like the packaging will have been made from a flat piece of card, which has then been cut up into bits that then can be made into a 3D shape, which is amazing. So we're going from 2D to 3D. And then also think about 3-dimensional design. So we think about, why are Apple things so kind of coveted? It's because they look good,
the aesthetic,
and they're using 3D shapes and the way that humans like things that look pretty to do that. And that's generally, there's a lot of maths in how to design something aesthetically, and I think that's something that I'd really like to kind of build into my teaching more, but I realise that time is quite tight.
I know, because again, as teachers, we try and, as much as possible, link it cross-curricular. The more you can, the more they see, well, actually, I can see why 2D and 3D shapes are actually important for the real world in terms of understanding. If I look at a building, or if I look at a swimming pool, to work out the capacity for that, or even if you're like cooking a meal and you're looking at a saucepan. So that might sort of lead us into the last couple of minutes in terms of discussing the common issues, because I find, again, actually, there's some students who really love the numbers part of maths, like anything that's, rearranging equations or substituting numbers into a formula, they really work well. But when it comes to shape and space, some people think, I haven't got a visual mind. And on the other side, you get people that suddenly come to life when you do 2D and 3D shapes, because they suddenly find their sort of arty, creative brain kicks in.
Yeah, but I think that's something that I think as teachers, and also I think parents, the more you get the students, the young people to play around with the shapes in real life, whether that be, drawing things or creating things, crafts is based on shape type thing. And also, as we talked about this before, there's so many dynamic geometry programs that can bring like things that are 3D to life.
GeoGebra sort of style?
GeoGebra, Desmos, there's loads of simulation stuff as well that can really bring things that look quite flat and a bit dry, bring them to life, which is kind of where there's so much scope now, more scope now than there used to be.
Like in the 90s when we were in school,
yeah,
shape and space, 2D shapes, 3D shapes was literally just a piece of paper. Teacher would have something on the board, or an acetate or overhead projector,
or a blackboard and chalk. So now like there's almost the sky's the limit with what you can do, and I think if we can bring it into more real life stuff, that's the key. I think that takes us now to puzzle time.
Puzzle time. So first, before we start, so in 1974, there was a craze, a mania, for a 3D-based puzzle by a Hungarian man named Erno, and it used to be called the Magic Cube.
Right, okay.
What's this called?
Oh, wait a minute. It's B with an R.
Yes, God.
U-B-I-X. Rubik Cube.
Did you say X?
K, I meant K.
Correct answer, wrong spelling. Yes, Rubik's Cube. So, for our puzzle, you're building a cube that looks like a Rubik's Cube.
Mm-hmm.
And the dimensions of this cube are 5 blocks wide, 5 blocks long, and 5 blocks deep.
Not 3, 5.
5, yeah.
Okay.
5 by 5 by 5.
Right.
And if you dip this total cube in a tub of paint, we'll call it claret and blue because I'm a West Ham fan, but it can be any colour paint, not discriminating, on the outside of the individual faces will become painted.
So the surface area is covered.
Yes, exactly. Well, technical language. So your question is going to be is, how many of the individual cubes will have paint on their faces?
Right, okay. One more time, please.
So we've got a cube.
Yep.
That looks a bit like a Rubik's Cube.
But bigger.
A bit bigger. And the dimensions are 5 wide by 5 deep by 5 tall.
Sure.
And you dip this cube in a tub of paint, and only the outside of the individual faces have become painted.
Totally covered.
Totally covered. So your question is, how many of the individual cubes will have paint on them? Because obviously some of them on the inside won't have paint.
Oh, you've blown my mind. Okay. This is real thought here.
I need unblown minds by the end of this episode, okay?
Right, okay. I'm thinking. So, we'll go through the puzzle solution a little later after we've heard from our special guest, Catherine Breslin.
Catherine's a machine learning scientist, and she's currently a consultant specializing in voice recognition technology.
I met her a little while ago to find out more about her job, the maths within machine learning, and women role models in tech.
Hi, my name is Catherine Breslin. I work as a machine learning scientist and a consultant. It means I help companies who want to use speech and language technology in their business. So that's things like speech recognition, language understanding, text-to-speech, all these technologies which exist around voice.
Wow, okay, so technology and voice.
Exactly, yes.
And so how did you get into that?
So a long time ago when I was a teenager, I remember my dad brought home some computer software which you could talk to and it would write down what you would say. And at the time I thought that was amazing. I'd never seen anything like it before, but I didn't really think about it until much later when I was at university. And I had gone to university to study engineering. In my fourth year of my course, we started doing topics in machine intelligence and artificial intelligence. And it was during that I thought back to the software, the dictation software, and I thought, actually, I really want to know how this works. And so I decided to take those courses in my last year of undergraduate and then go on to do some more graduate study.
Right.
So I did a master's and a PhD. And then I started working in the field doing research.
Wow, okay. And so you work in the field. So what kind of things did you do?
So I started off by doing a lot of research into how to improve voice recognition systems.
Right.
So I worked in university and then I also worked in some companies. And for a long time, voice recognition technology wasn't really used for that much stuff. But in the past 10 years or so, there's been a big change in the number of people using voice recognition technology and voice technology. And so there's a lot more demand for building products. And so in the past few years, then I moved and I started to work on products that use voice.
Okay, right. There's a lot more of those now,
There's a
aren't
lot
there?
more, yes.
Right, okay. And so kind of how do you go from the talking to it being digital and then a computer understanding what that means?
So in speech recognition, you're trying to go from the audio, the recording of what someone said, to the words that they said. This is your best guess of what words that they've said.
Right, okay.
So a lot of this involves a lot of probability.
Right.
Yeah, and so we have 3 parts to the system that we build. The first one takes little segments of the audio, and from those segments of the audio tries to predict what the sound is. So we break the audio down into what we call phonemes, things like k and th and a, the individual building blocks of sounds.
Yeah.
The ones that you might be taught in phonics at school, for example. And then from there we have another model which takes a list of words and it tells you how those words are pronounced in these sounds. So we might tell you that the word cat is pronounced k, a, t. And if words have lots of pronunciations like read and read, we have both of those pronunciations in this model. And then we have a third part which tells you how those words are strung together.
Right.
So it might tell you that if you say, hi, my name is, what you expect to see as the next word, the most probable next word could be Catherine, but it's unlikely to be cat.
Okay, right. Wow, so there's a lot going on there.
Yeah.
But and also accents must be quite tough.
Accents are tough. There's a few ways to handle accents, but what we do is we learn these models from a lot of data. And this is a big topic at the moment, is learning models from data. And so what we do is we just have a lot of data of different people speaking in different accents. And from that, we can kind of learn how people speak differently.
Oh, gosh, wow. And so, so you it's from engineering you kind of got into this.
Exactly, yeah.
And so you're currently working as a consultant.
That's right.
And then I sort of hear that you did some work on Alexa. So what kind of stuff was that?
So I joined Amazon just before Alexa launched. And over the last the few years after that, I was really lucky to be able to work on Alexa and to be able to be involved in the team who was growing and scaling it up.
And so, I mean, now that's kind of revolutionised how a lot of people work with computers, really, isn't it, now, you know? So where do you see the future of this type of technology?
I think there's a lot of interest in how we can use voice in different ways, and we're starting to learn how to understand much more natural language. So as well as understanding the words someone has said, we also want to understand a little bit about the intent behind them.
Okay,
so
right.
It's no good just knowing what someone has said. You need to know something about what that means in the world.
Context.
The context. Yeah. So not just what the literal meaning of it, but what it actually means there. Because if I say something to you now, it probably means something different if I say it to you in the school or at the doctor's.
And things like sarcasm can make it hard.
Sarcasm is very hard for computers to handle. Yes.
Yeah. Right. Okay. Wow. So you're a woman in tech. We spoke to Danielle Newnham a while ago, who is a wonderful woman doing great stuff with F equals and stuff. And she sort of said when she was working in tech that she didn't see many women role models. Was that the same for you?
I think so, yes. Technology does have an issue where there are very few women, especially in the senior roles. Mm-hmm. I think voice and language is slightly more female friendly. I think a lot of people come into voice and language technology from linguistics backgrounds.
Oh, okay.
So we do see a few more women coming in that route. And while they may not have the same kind of computing jobs, we need a lot of linguistic expertise in our systems. So that's one way I see a lot of women. But I think it is true that there are not so many women in the core technical roles.
Is there anything you think that, you know, schools could do to improve that? I mean, did you have a generally quite positive experience with kind of getting into tech and everything?
I did, yes. I think I had very positive teachers when I was at school. Right. My maths and physics teachers especially were the ones who sort of inspired me to go and look into physics and maths and engineering as degree subjects. So I was very lucky that they supported me, and my parents also were very supportive and very happy for me to look into engineering and maths as careers. I think when I was at school, it wasn't cool to be a maths geek. That didn't bother me too much, but I know it does bother a lot of people, and it is one of the things which puts a lot of girls off science and engineering careers, is the perception that they are boring and very technical and very mathematical careers is not for them.
So what do you think would make it cooler?
I think one of the things that I see is that there is not... It's very hard when you're studying maths at school to see how it can be used in the world. I think it's very difficult for... Technology is changing so fast, and it's all being used in all this new technology, and it's very difficult to keep up and to be able to translate what's being done in industry into something that children can understand.
Yeah, and that's hard for maths teachers to really get abreast of what's going on. Really.
It's hard for us, even in the industry, to keep track of what's going on. And so for teachers to be able to do that, I think is really difficult.
But you think that, but actually you kind of think that would be a great way of getting kids properly engaged and understanding why they're doing it.
Yeah, I think a lot of children do want to go and work on something which has a big impact in the world. They want to make lives better for people. They want to improve the world. And showing them how maths and science can contribute to this is definitely something we should be doing.
So you do some stuff in schools, don't you, sometimes?
I've been into schools and I've talked to children about what I do, and I've run some coding workshops for teenagers in the past.
We're thinking about the way sort of maths topics are delivered and, you know, trying to make it as inclusive and as accessible as possible. Do you remember your favourite maths subject at school? And if so, what was it and why?
Probably mechanics. When I was doing A-level maths, I used to like mechanics because you could see exactly how it's used. You could see how the physical world translated into the mathematical world. I wasn't that keen on probability and statistics when I was doing my A-levels, which is weird because then I went into this career which is heavily based in probability and statistics, and I got much more comfortable with that part over time. But I think I always liked the bits of maths which were applied.
Oh, right, okay. And so tell me a little bit more about the probability element of what you do, because that's kind of, I think what people can understand the whole idea of the mechanics of something, you know, and then the technology part, but like the probability part, what kind of things does that entail?
In artificial intelligence is a big area at the moment, and one of the things which has driven a lot of the advances in the past few years is a field called machine learning. So machine learning is a set of algorithms which are where we are trying to learn things from data. So we might be trying to learn, for example, how to transcribe speech automatically from data, or how to mark some email as spam or not spam,
Right,
or
okay.
how to tell you what object is in an image, whether it's a cat in an image or a teapot in an image.
Wow.
And so all of these are based on large sets of data. And so we're really trying to learn a model which is going to estimate the most likely thing in that task. So
Right.
you're trying to estimate the most likely
Scenario.
object in an image given the picture, or you're trying to identify the most likely set of words that have been spoken given the audio. And so it's all based on the probability, and you learn those probabilities from a big set of examples, a big set of data.
Wow, so it's not exact, but it's kind of as close to exact as you can get in like the real world. It's kind of going from experimental probability to the other way around, theoretical.
Yes, so
Yeah.
it might be going. So we take a lot of probability theory and we apply it to real world examples, real world data, and it's not an exact science. Probability is not an exact science, and so this is why a lot of artificially intelligent machines make mistakes. It's
Yeah.
because we are just doing a best guess, and in some cases that's really, really accurate.
Yeah.
And in other cases, some tasks are just so hard that it's not that accurate. But that's what we're trying to do.
I'll tell you what was a mistake.
What was a mistake, Bobby?
In Terminator 2, when they decided to leave the arm, should have destroyed the arm, machine learning, artificial intelligence, and the world has changed.
There were a lot of schoolboy errors in, I think, the Terminators, because that film stayed with me. And I mean, I think what Catherine's doing and, you know, where AI is going is so exciting, but also kind of terrifying, right? Because, you know, the potential is kind of huge. But you cannot get over the fact that with some of the technology now, our lives have changed so hugely, and we've become really quite a lot easier, you know?
But even like the way our smartphones sometimes will suggest, you need to leave now to get to work. My one actually tells me when I should leave.
Yeah.
And that's based on, it's obviously got information on an average day when I leave for work, how long my commute normally is, and it will look at, there's traffic or there's tube delays. And and that's amazing because it's real life probability and statistics. It's taking data, saying, the chance of this happening is 70%, and if that happens, then
this will happen.
Effect, yeah.
And that's what's crazy as well, the whole idea that there's like a bank of words that the technology has to refer to. So it will be like hundreds of or thousands of people saying the word cat, so that when someone does say cat that's not in that database, they're like, that's cat.
Cat.
I mean, and if you talk strangely, it makes it even more, incredible that that even works. Do you know what I mean? Cat.
Thank you, Catherine.
Thank you for opening our eyes to the magic of voice recognition. So I think on that, Bobby, we should go back to your puzzle. I mean, this has fried my head, I'm not going to lie to you, but I've done a few diagrams and I feel a lot better about it. So could you want to remind us of what the puzzle is?
Okay, so you got a cube, a bit like a Rubik's Cube.
Yep.
The dimensions are 5 by 5 by 5. So 5 long, 5 tall, 5 deep, as it were. And you dip this cube into a tub of paint. And on the outside of the faces of the blocks get paint on them. So your question is, how many of the individual cubes have paint on their faces?
Right.
Deep breath.
I'm sorry, I'm really proud of my diagram.
Oh, visual.
And I had to really think this through because I'm not very good, I think, doing stuff in my mind. I have to write them down. Like, I have a few issues with left and right. Should I admit that?
You don't drive, do you?
I do. But then I also...
DVLA, you didn't hear this.
I mean, I can work it out. I just have to think a little bit about it, you know? So, obviously, I will be putting my solutions on our Instagram and Twitter at MathsAppeal. But I did have to draw something to really get my head around it. Okay. So, how I started, Bobby, was I drew my cube 5 by 5 by 5. Then, the whole paint thing blew my mind because I realised that you do one side, right, of the cube, and that one side touches other sides.
Mind blown.
Okay, so I had to break down my cube into front, back, and then left and right, and then bottom and top. Mm-hmm. Okay, because then I had to sort of like taking cubes out.
Yeah.
Okay, of our problem. So I took the front and the back all of the cubes in the front and all of the cubes in the back have been covered once. Yep. And so that was 25 cubes of the front, 5 by 5, times 2, because that's the front and back, 50,
Okay.
right? So then once I've done that,
Yeah.
I'm then going to look at my left and my right. And what's happened here is the sides of my left and my right have already gone. So like a whole row of 5s, 2 rows of 5 have gone because they've been covered in the front.
Okay,
this is
got you.
bonkers, right?
Yeah.
So then the new cubes that are covered are 3 times 5.
Okay, yeah.
And so that's 15, and that's 2 times 15, which is 30.
Yep, so we got 20, 25, 25, 15, 15.
Thank
Look,
you.
By the way, if you can see into our studio, it looks like I'm milking a cow because I'm demonstrating what this looks like, but I'm not.
Huge cow, but yeah. Thank you, Bob. It's helping me as well. And then the top and the bottom,
Yeah.
the outside edge of the top and the outside edge of the bottom have all been covered already.
Yeah.
Those cubes have been covered already. So the only ones that haven't been covered, that haven't counted, are the 3 by 3 in the middle.
Okay, yeah.
Yeah, and then the same at the bottom.
Uh-huh.
So that's 9 and 9.
Yeah.
So then I got a total of 98 cubes.
Perfect.
Oh my God, that was really intense.
You know, there was a simpler way.
Oh, no. Well, hey,
But the thing is,
share me.
Okay, so we've got a 5 by 5 by 5 cube, yeah?
Yeah.
So imagine inside of that.
I'm sorry, I have to just, the fact that you're probably going to say this in one sentence is stressing me out, but
But I'm so impressed that you were dedicated, persistent, diligent, and you got the right answer. Your method is much harder.
the long way.
Yeah.
It's cool. Okay, tell me,
Okay.
Bobby. I'm sitting down, head in hands. Go.
Okay, and then inside this cube that's 5 by 5 by 5, you can imagine like there's a 3 by 3 by 3 right inside it, isn't it? That doesn't touch the outside.
Yeah.
So the big cube is 5 by 5 by 5, that
Yeah.
is 125.
Right.
The small cube inside is 3 by 3 by 3. 27. 125 minus 27 is
It's 98.
there you go. There we go.
Oh, wow.
It's 2 methods. So I thought you were going to do this method, and I was going to explain actually there's a more complicated, more fun way that really gets you thinking about. But the thing is, yours showed, honestly, like you had to think quite logically because you had to say there's 5 and 5, 3 and 3. Mine's like a cheats method.
Oh, do you know what? It's good. I mean, this is the thing. There are different ways of skinning a cat.
Exactly.
Or milking a cow.
Cat.
Cat. There's different ways. And I mean, I feel I totally understand my way, but I also understand your way.
Yeah.
Yours is definitely more efficient.
I guess we could, if we scaled it up to a 6 by 6 by 6 cube or a 10 by 10 by 10 cube, like a 10 by 10 by 10 cube.
Yeah.
If you dipped it in paint, it'll be 10 cubed minus
8 cubed.
Yeah.
Oh, now you've opened my eyes.
Yeah.
Bobby, you are the puzzle master.
Puzzle master.
Oh, well, okay, we'll make sure that both solutions are up and you can see I took the low road and Bobby took the high road. Okay, well, before we go, have you got a maths fact for us taking from your book, The Life-Changing Magic of Numbers?
So the cube or dice, and this is actually a really special shape because this is something called a platonic solid.
Oh, yes.
Yes, and there are only 5 of these. So people are going, but Bobby, Susan, what's a platonic solid? So the fancy definition is that this is a 3D shape where each face is the same regular polygon and the same number of polygons meet each other at each vertex. What does that mean in English? You're like, English. Basically, it just means a 3-dimensional shape with different sides to the shape, and every side is the same. And
So every face?
Yeah, and every corner looks the same, essentially like a dice. And the most famous one is the dice, 6 sides, all a square and all exactly the same, and all the corners look the same. Mm-hmm. Then we've got the smallest one is the tetrahedron. Mm-hmm. So there's 8 triangle faces.
I think tetra means 4.
Yes, you're right. 4 triangle faces, thank you.
You're
Octahedron, 8 triangle faces. That's revenge for the other puzzle, isn't it?
Indeed it is.
Then the dodecahedron is 12 pentagons, and the icosahedron, 12 triangular faces. And these are actually the only shapes that you can make using regular polygons. There's no other shapes that you can make.
There also, do you know why? This is one of my favorite. I like this fact. Like I love the platonic shapes, but it comes from Plato because supposedly they represented the elements of the universe. Are we going to say that already?
You're reading my sheet. Well, I was going to say my mind, but you're sitting far away from me, so you bringing knowledge.
So you continue. I'll stop taking your facts from you. Go on, Posy.
Yeah, no, that's right. So we've got 5 platonic solids, and these are solids that are made up of the same shape all the way across.
They're beautiful.
They're really beautiful. And essentially, I think one way of thinking about it is, if you could make a dice with all of them. You could make a 4-sided dice, 6-sided dice, or 4-sided with a tetrahedron, then a 6-sided with a cube, then an 8-sided with the octahedron, then a 12-sided with the dodecahedron, and a 20-sided with the icosahedron. And they'd all like sort of have an equal chance of landing on any surface.
Oh, wow. Well, I will obviously on our Instagram and Twitter at Matt Appeal put images of those, because I just think they are beautiful shapes, and they also represent the elements of our world, don't they? I think the icosahedron is the universe.
Yes, you are well versed in this.
This is some little fact that I know.
Nominate Okereke.
Thank you. Buzz.
Next week is the final podcast in the series.
Oh my goodness.
Cry, tears. So I better make sure that the puzzle is a good one.
No pressure, but you must.
And we'll chat about measure.
And our guest is Zoe Griffiths, a maths communicator that works for an organisation called Think Maths that visits schools to run interactive and engaging maths content to excite and engage students in mathematics.
Before we go, we just want to say a huge thanks for your support. And thank you as well if you've done our puzzles and tweeted your answers. There are loads of people to mention, but a few names are Bill Logan, Dr. Edward Bear, Gwyneth Slavin and Will Lord. So thank you for sending in your puzzle solutions.
And also a big thank you if you've shared your favourite online maths resources to help Bobby and myself put together an online maths resource top 10. Some suggestions have been from A. Ahmed, Corbett Maths and Pixie Maths. They're fantastic and they're free. Also, Mrs. G says Resourceaholic, Mathbox One, Don Stewart and Integral are her favourites. And also Alice Yelf says that Times Table Rockstars is great for the young ones. So there's some great suggestions there for us, aren't there, Bobby?
Loads. And the teachers, we love them.
So again, thank you so much for listening to Matt Appeal with me, Susan Okereke and Bobby Seagull.
The music's composed by Kelly Okereke, the image design is by Calix Davis, and the producer is a wonderful Jenny Nelson.
You did it. 5.